Okay, it seems that we are live on YouTube, and before we start, let me share my screen. As usual, let me first announce the next week's seminar. Okay, next week we are going to have Professor André Saraiva, and I'll just let you know that we're gonna start at a slightly different time because our next week guest is in Australia right now, so it would be a little bit difficult for him to make it at 4 p.m. So we are going to start at 7 p.m. and André is going to talk about the route to a million qubits. And he's now he's former from the Federal University of Rio and now at the University of New South Wales, Australia. And today it's a okay. It seems that I cannot move my screen. Just 1 second. Sorry about that. And today we have the honor to have Professor Axel Hoffmann from University of Illinois, and I kindly asked Professor Antonio Azevedo to introduce him. Antonio, please.
Thank you, Rodrigo. Good afternoon, everyone. It's a pleasure to introduce Professor Axel Hoffmann. Professor Axel got his PhD degree in physics from the University of California in San Diego in 1999. Later, he worked some time at the Los Alamos National Laboratory as a postdoctoral fellow. And in 2001, he joined the Argonne National Laboratory as a staff scientist and became, in 2014, the senior group leader at the magnetic film group. And later in 2019, 2 years ago, he joined the Department of Material Science and Engineering at the University of Illinois at Urbana-Champaign as a founder professor. Axel works with many things and in magnetism related subjects, including basic properties of magnetic heterostructures, spin transport in different geometries, and magnetization dynamics. And he is one very known guy. Always he's in conferences, giving invited talks, and at this moment he's associate editor for the Journal of Applied Physics, and he also is a fellow of the American Physical Society and American Bacon Society, and also IEEE. Axel visited Brazil many times, at least three or four, I don't know. And Axel, it's really a pleasure to have you here. Now it's with you.
Yeah, thank you, Antonio, for the nice introduction. Oops, now I pressed the wrong button, but it's really a pleasure being with all of you, even if it's only virtually. Antonio is correct. I've been to Brazil many times, more than 3 times, at least half a dozen times. I don't know, I haven't counted for sure, but anyhow, it's nice even just being virtually with you here. And so when I got invited, I asked what topic might be of biggest interest. And so I'll talk about magnetic skyrmions, which behave like quasiparticles due to their topological properties. This is not necessarily our newest results. So some of you may have heard some of it. I know Antonio has seen some version of this, so he may not learn much new. But I hope for the rest of you, you'll still enjoy it and find it very interesting. So with that, let me get started. Oh, and by the way, if you have questions, do not hesitate to interrupt me. I'd be more than happy to discuss questions as we go along. You can also, if you find that easier, simply type them in the chat, for example, and I'll be happy to look at it there. Okay, so here's what I'll try to tell you about. First, I'll tell you a little bit what skyrmions are and how we can see them in magnetic multilayers. Then I will show you a mechanism by which we can generate magnetic skyrmions on demand, which we call blowing skyrmions, because it looks a little bit like blowing soap bubbles. And indeed, the physics is somewhat related to those processes. And then I will show you how the peculiar topology of skyrmions also affects their dynamics, the way how they move. And in fact, what you will see is that the dynamics of skyrmions can be directly related to the dynamics of rotating objects, like a rotating soccer ball, let's say, which I know is popular in Brazil. So, and then in conclusion, at the end, I'll have a few brief conclusions of my presentation. Okay, so first, let me tell you a little bit about what is still possibly new in magnetism, right? Because magnetism is a subject of human curiosity for thousands of years, I would say, since, I don't know, the Chinese used it as a compass and what have you. So a topic that's been explored for so long, for so well, the question is, what have we missed so far? Well, the interesting thing about magnetism is that it involves interactions both at the atomic scale, because you have exchange interactions that couple magnetic moments on individual atoms. So these interactions are characterized by very short length scales, fractions of nanometers, and the energies involved are very high, so resulting in dynamics that's very fast. And then at the same time, as anybody who ever played with magnets knows, there's also very long-range dipolar interactions, which can be macroscopic distances. So for the things that we do in our laboratory, that means larger than micrometers, let's say, and the dynamics can be very slow. And what makes magnetism such an interesting topic is that these interactions at these very different lengths and time scales can compete with each other. And that can give rise to a lot of complexity. Now, if you add into the mix other types of energies, like you can have anisotropies given by the symmetries of the crystalline materials that you work with, you can have spin-orbit interactions where the spin degree of freedoms are coupled to the way how electrons move in your materials. Zeeman interaction, which are the interactions of magnetization with external magnetic fields. Then once you mix it all together, you can have a wide variety of very complicated spin textures that both in space as well as in time. And here are just a whole bunch of examples. So I know, for example, Antonio is interested in spin waves and Bose-Einstein condensed magnons, for example. Today I'll talk about skyrmions. You can have all kind of other interactions that I won't really touch upon. Just give you, a quick, brief overview. Okay, so now the other reason why, sorry about that. Let me switch that off. Why what I'm going to tell you about is of interest to us is that it really has some applied motivation. Namely, as Antonio mentioned, I worked for many years at the Argonne National Laboratory, which is a laboratory funded by the Department of Energy. So there we had to think about how our work relates to energy. And so let me give you here my brief hand-waving way how what we do relates to energy efficiency. Namely, one of the issues that we're facing nowadays is when you miniaturize electronics, one big problem that you face with is heat dissipation. The issue is, as you make electronic devices smaller and smaller, the amount of useful currents that you want to use in your device goes as the volume of your material, while the amount of unwanted currents, leakages out of the device goes with the surface of your device. So by making things smaller, the amount of leakage currents versus the currents that you want to use becomes higher and higher. And so you have much more unwanted dissipation by making electronic devices much smaller. And this becomes like a real problem where the heat generation becomes hard to manage. And so here, jokingly, you can now prepare your breakfast when you do your physical simulations. Who knows? So the question is now, are there ways beyond the commonly existing electronic logic that we can do things better? And it turns out that using the spin degree of freedom may have some advantages there. So the way how we can use the spin degree of freedom may come in various ways. We can generate spin polarized charge currents, where we take a charge current and by passing it through a magnetic layer, the current will be carried mostly by one spin direction versus the other spin direction. But if you think about it in terms of energy efficiency, you still have the same kind of ohmic resistive losses that you have with ordinary charge currents. So just by making them spin polarized doesn't really help you. So then the next thing you can think of is, okay, well, maybe we can use pure spin currents, where one way how you can think of this is by having electrons where one spin direction moves in one direction while the opposite spin direction moves in the opposite direction. Now this way, you still move spin information from one side to the other, but there's no exchange of charges. Now, if you look at it compared to this cartoonish picture here, you transport twice the spin current with like 2/3 like 2/3 of the electrons involved, but you're still moving electrons through the material. So it's not clear that you really gain much in terms of power dissipation. So then you can take this one step further and say, okay, well, how about we use magnetic excitations in magnetically ordered systems? And these can be spin waves or magnons. And spin waves or magnons can also carry spin information and propagate it from one place to another. And so now we have a physically very different mechanism of transporting information. And so maybe that is a more energy efficient way. And so what I will talk about today is essentially a mixture of concepts that involve pure spin currents and information encoded in magnetization structures. So the magnetization structures will be more static in our case, where it's the Skyrmion spin textures, and we use pure spin currents to move them through the material set. Okay, so with this, let me talk about magnetic Skyrmions. If you're interested in what I'm telling you today, then I can highly recommend this review that we wrote a couple of years ago, which discusses many of the aspects that you find in the presentation today in much greater detail. So first, you may wonder, Skyrmions, that's a curious name. Where does this come from? Well, it comes from this guy, Tony Hilton Royal Skyrm, who was a theoretical physicist. And by all accounts, he was overall a rather unlucky guy, if you want so. This is a picture where he was very young in his 20s. So at that age, he got hired by Rudolf Peierls to work at the Manhattan Project, which was a project at the Los Alamos site, which later became the Los Alamos National Laboratory, where in the United States they developed nuclear weapons. So it turns out he was one of two British people. The other one that was hired was Klaus Fuchs. He shared an office with him. And it turns out Klaus Fuchs was actually a spy for the Soviet Union, who told the Soviets then how to build a nuclear weapon. But having shared an office with Klaus Fuchs was fortunately not the end of the career from Tony Skyrm. He went back to the US and he was working then on high energy physics. He developed models how to describe baryons, which protons, neutrons essentially, as topological solitons of a vector field known as the pion field. Now, but it turns out in the 60s, if you worked in high energy physics, you got much more interested in something else, which was known as quarks. So this model didn't get much attention at that point. So later, about 2 decades later, the Skyrm model finally gets some more attention by particle physicists, yet for them to be distracted yet again by something else, which was string theory. So Tony Skyrm did get the huge medal then in 1985, which is like one of the highest scientific awards in the United Kingdom. But he died 2 years later during surgery that didn't go well, and so he never became a member of the Royal Society. Anyhow, in any case, the ideas from Tony Skyrm, he certainly didn't put them in the context of magnetism, but in the 70s, it was already realized that similar topological solitons could be in the vector field given by the magnetization of materials. And in the mid-90s, this was then also discovered experimentally. Namely, in not the mid-90s, in 10 years ago, in 2009, sorry. In 2009, a group of scientists in Germany and Switzerland were studying a well-known helical magnetic system known manganese silicon. And manganese silicon had been known for decades, and it was known to have a somewhat complex phase diagram, where as a function of field and temperature, the magnetization would order slightly below 30 Kelvin. And then at low fields, you had a magnetization that's helical, where the magnetization rotates around. Then if you apply high enough fields, this helical structure becomes conical. So the magnetization all sits on the direction of a cone with a net magnetization in the field direction until the cone angle closes at high enough field, it becomes field polarized. But then it was also known that at high temperatures, close to the ordering temperature, and at intermediate fields, there was a different magnetic structure. And for many years, it wasn't clear what this was, and it was just called the A phase, where A stood for anomalous, because people didn't know what it was. But then it turns out this group in Switzerland and Germany did some small angle neutron scattering on manganese silicon. And when they did the experiment, they actually oriented the field in the wrong direction, or the crystal in the wrong direction. And they saw this 6-fold scattering pattern, which was not consistent with the crystal symmetries of the crystal. And so they were wondering what this was about. And after a good amount of head scratching, what they figured out is that the magnetic structure that's associated with the scattering pattern is given by a lattice of magnetic skyrmions, where magnetic skyrmion is a magnetization structure where most of the magnetization is aligned with the applied magnetic field. But then you have in between areas where the magnetization is opposite to the applied magnetic field. And in between, the magnetization winds around this opposite magnetization. And what makes this unique is if you look at an individual plaquette of such a magnetic skyrmion, then it has a distinct topology. And so you can see this if you take the magnetization structure of such an individual skyrmion and you project it on a unit sphere by taking the magnetization at the center and project it on the south pole, and taking the magnetization on the outside and projecting it on the north pole, you see that the magnetization winds around once around the whole 360-degree sphere. And so in other words, the magnetization wraps the sphere exactly once. And this is very different from either the helical, conical, or field polarized magnetic state, where it doesn't wrap the sphere once. So there is a topological distinct transition there. And mathematically, you can describe this topology by defining a so-called topological charge, which is given by the integral over the whole space, taking the magnetization times the spatial this combination of spatial derivatives of the magnetization. And when you do this for this magnetic structure as such, you see that the topological charge is either plus or minus 1. Notice that this topological charge is odd in the magnetization, as it is defined in this case. So if you reverse the magnetization, you also change the sign of this topological charge. So the different signs do not mean drastically different magnetic structures. It's just the reversed magnetic structure. Okay, so what is interesting is that let's go back and see what are the ingredients that give rise to these unique magnetic structures. Okay, so let's start with something that we know very well. Let's say we write down a simple Heisenberg Hamiltonian where nearest neighboring spins are just coupled via an exchange interaction. And if this exchange interaction is positive, we know what the solution of this is. What we end up with is a state where all spins are pointing in the same direction, a normal ferromagnetic state. Now, if we have now special type of materials where inversion symmetry is broken, then we can also have a different type of exchange interaction called an antisymmetric or chiral exchange interaction or Jaluzinski-Maria interaction. While the Heisenberg exchange interaction depends on the dot product, the Jaluzinski-Maria interaction depends on the cross product of neighboring spins, and therefore it has a built-in chirality. So when you exchange the two spins, you get a negative sign by exchanging it. So the Jaluzinski-Maria interaction now wants to have spins that are preferably perpendicular with each other, while the Heisenberg exchange interaction wants to have them parallel. So if you have both interactions in your system, what will happen is that the spins are neither parallel nor perpendicular, but they're at some intermediate angle, where the intermediate angle is simply given by the relative strength of the Heisenberg and the Jaluzinski-Maria interaction. And so you get a spin spiral that looks like such. And this is the helical structure that you see in manganese silicon in low applied fields. Now, if you look careful, what you see is that you have as many spins pointing up as you have pointing down. So it's symmetric in that respect. You can break this symmetry by applying an external magnetic field that gives preference to one spin direction. And this is when you then form skyrmions. Essentially, you can think of a skyrmion as the interference of several of these helical waves with different propagation directions. So you then have most of the magnetization aligned with this magnetic field, and then individual skyrmions in the center. So what it comes down to is that having a chiral exchange interaction really helps in forming these skyrmion structures in magnetic systems. Now, in manganese silicon, this comes about because the crystal structure has broken inversion symmetry. Manganese silicon is actually one example of a broader family of materials called B20 compounds, which are cubic materials where it's a 50-50 alloy, where along the 1-1-1 direction of your cubic unit cell, you have alternating layers of one material versus the other. And just by visually inspecting this crystal structure, you see that inversion symmetry is broken, because if you have manganese here, you have silicon on the inverse symmetry related side. Now, besides breaking inversion symmetry via crystal symmetry, you can also break inversion symmetry simply by having a layered structure, because as soon as you have an interface here, there's automatically a breaking of inversion symmetry. And it turns out that by using a ferromagnetic material and you combine it with a second material that has strong spin-orbit interaction, and large spin-orbit coupling is prevalent in heavy elements, you can get very strong chiral exchange interactions at these interfaces. And this has been demonstrated now by a whole bunch of different structures, let's say cobalt and platinum, or permalloy, which is a nickel iron alloy that we like to use in magnetic materials with tantalum, and so on. Lots of different combinations there. This gives you much more flexibility in designing the magnetic materials that you want to work with. So now that we know that we want to generate these chiral exchange interactions, let's go back once more and think about how the topological charge is of interest of these structures. It turns out that the topological charge of these magnetic structures actually has unique physical implications. Namely, the topological charge associated of these spin structures results in an emergent magnetic fields for electrons that move in these spin textures. And the hand-waving way how to understand this is, if you have an electron that moves in this spin texture, if the exchange coupling between the electron and the local magnetization is strong, it means that as the electron moves, its spin will always be aligned with the local magnetization. And so as you move it through this inhomogeneous spin texture, the spin of the electron moves around. Or in other words, the spin of the electron feels like it's exposed to a virtual magnetic field that makes its spin precess. And the magnitude of this virtual magnetic field is actually given exactly by the same formula here as the one for the topological charge. And so it's essentially the topological charge multiplied by the flux quantum of the magnetic flux. And so the field is then the flux quantum divided by the area of our skyrmion. And so if we have skyrmions that are tens of nanometers in diameter, this corresponds to then fields that are of the order of 100 Tesla. And so one interesting consequence is that when you look at transport in these magnetic materials, you get very strong Hall effects, much stronger than just by the applied magnetic field itself. And that's given simply by the unique topology of these magnetic structures. Now, the interesting thing is, as the electron is deflected by these emergent magnetic field, this actually creates also back action on the skyrmion, where the skyrmion moves then in the opposite direction. And it was noticed early on that in manganese silicon that this results in motion of these skyrmions for very low fields, for very low current densities. Before magnetic skyrmions were discovered, it was already known that you can move magnetic domain walls with electric currents. But if you compare the electric current densities required for moving domain walls, they are 6 to 7 orders of magnitude higher than the ones that you need for moving skyrmions in manganese silicon. So this then indicated that maybe using skyrmions is a very good way of encoding magnetic information and moving them via electric means. Now, I have to say, if you use very small currents, the skyrmions also move very slowly. So it turns out this in itself is not necessarily so useful. The other thing that makes skyrmions nice is, since they are a local spin texture, if you move them through an extended magnetic film, they can easily move around defects in your material. Unlike a domain wall, which may go across the whole length or width of your material, a skyrmion is just localized on the inside and therefore has much more flexibility to avoid defects. And in fact, if you look at micromagnetic simulations, that seems to be the case. So here you see a micromagnetic simulation where a skyrmion just moves around the defect that is cut into a wire, a magnetic wire here, for example. And only at very small current densities, the skyrmion gets stuck at this defect. So this becomes an interesting, because there has been an idea of how to encode information in magnetic textures, namely in magnetic domain walls. And then you move the magnetic domain walls using electric currents in a magnetic wire. So it's a little bit like your old video tape recorder or your audio tapes that some of you may be familiar with. But instead of moving the whole tape, what you would do is you move the magnetization inside of a magnetic wire. And this is a concept that was developed at IBM by Stuart Parkin, as known as racetrack memory. And as I said here, if you have a magnetic domain wall, if you have a defect somewhere in the wire, the whole magnetic domain wall has to cross the defect. If you use skyrmions, maybe you have less of an issue there. And so you can imagine that you use the same concept and encode information in the presence or absence of skyrmions, and then you move them coherently with electric currents. So this is one of the goals ever since the discovery of skyrmions. So in order to be able to do this, though, what you have to have is, you have to have a mechanism by which you can generate magnetic skyrmions on demand. And it turns out one way how you can do this is by injecting spin polarized currents into your skyrmion material. So here this was demonstrated in 2013 by a group in Hamburg who used an iron palladium alloy on top of an iridium substrate, where they locally used an scanning tunneling microscope tip to inject spin polarized currents, and then they can generate a skyrmion where previously there was none. And they also showed that by reversing the current, they can eliminate the skyrmions. So this means, this showed that you can on demand create or delete skyrmions. And so this then really means that maybe we can use topological charge instead of electronic charge in information technologies. Okay, so the one problem with this is that using spin polarized scanning tunneling microscopes is a really difficult experimental technique. There's maybe a handful groups in the world that do it very well. This experiment was done at very high fields at very low temperatures. Also, it wasn't clear whether these skyrmions were actually mobile. And so at that time, we were thinking of looking in different ways how to generate skyrmions. And so what we discovered is a way how to generate skyrmions in a process that is very similar to blowing soap bubbles, only we blow magnetic skyrmions in the lab. So what do? We start off with a cobalt iron boron film, which we have on top of tantalum and capped by tantalum oxide. And so by having different interfaces on both sides, we break the inversion symmetry, and so we get the Jaruzelski-Moria interaction. But also we know that having an oxide on the top gives rise to a perpendicular magnetic anisotropy of the cobalt iron boron. And tantalum is a very good material for electronically or manipulating magnetic states in the cobalt iron boron via electric currents. So first, let's look at this perpendicular anisotropy. If we measure the magnetization versus field for this cobalt iron boron layer, we see that if we apply the field perpendicular in this direction, which is shown here by the blue data points, that it takes a very small amount of field to saturate the magnetization in this direction. While if we apply the field in the in-plane direction, which is shown by the red data points, we need a much higher magnetic field to saturate the magnetization that way. So in other words, the magnetization likes to point in the out-of-plane direction. And when we do so, if we look at magnetic domains without an applied magnetic field, we get typical domain structures. So this we can do via magneto-optic imaging. And here the white and black regions are areas where the magnetization points up or down in this thin film. And if we now apply a magnetic field in one direction or the other direction, we make either the bright domains bigger or the dark domains bigger. Okay, so this looks quite a bit like these helical structures that we have in manganese silicon, except a little bit more disordered. And what we do now is, remember with the manganese silicon, we want to have a little bit of a field to favor a one spin direction. So we do exactly that. We apply a small amount of field so that we have only small regions of opposite magnetized magnetic structures here. And then what we do is we take this kind of structure and apply a current through this narrow bridge here. So now we have a field. So we have these small domain wall structures, the band domains here, and we pass an electric current in this direction that pushes the magnetic domain through this constriction. And when we do that, what you see is that here at the exit, we do create magnetic bubbles, magnetic skyrmions. And you see they do behave like individual particles. They have repulsive interactions where new skyrmions push the old ones further to the right. If you have a keen eye, you see that they mostly move towards the upper right corner. We'll get back to this in a moment. So what is going on here? So if we look at this carefully, then what we see is you have to understand two physical phenomena to understand what you were just seeing. One is what is known as the spin Hall effect. If you take a non-magnetic material and you pass an electric current through this non-magnetic material, then because of spin-orbit interactions, you get different scattering for spin-up and spin-down electrons relative to the current direction. That results in a transverse spin imbalance. And if you now take a material where these spin Hall effects are very pronounced, let's say tantalum, and combine it with a magnetic layer, let's say cobalt iron boron, then the spin accumulation that you generate in the tantalum that's perpendicular to the current direction can be injected into the ferromagnetic layer, and it can put a torque on the ferromagnetic layer that way. And so what that will do for you is it allows you to use an electric current to manipulate the magnetization in this ferromagnetic layer. And this works best, the torque is biggest when the current is actually in the same direction as the layer, you're parallel or anti-parallel to the magnetization in this layer. Okay. So if we now have a magnetic layer with a perpendicular anisotropy and Jaluzinski-Moriya interaction, where the magnetization likes to curl around in a well-defined direction, then it has been known that this combination of spin Hall effects with Jaluzinski-Moriya interaction gives rise to very efficient torques that you can move domain walls very nicely. Because essentially, whenever you have this magnetization now in the direction of the current puts a large torque on it, which twists the magnetization, and so it moves this twisted magnetic structure through the layer. And this is what happens in a narrow magnetic wire, where you have a domain wall going across the whole direction of the wire. But if you now have a more extended film where you have such a band domain, remember that the torques from the current were large when the current is collinear with the magnetization in the domain wall. So here there's a lot of torque, but here on the side walls, there are no torques at all. So by passing a current through a magnetic film with such a band domain, all that we do is we pull, we extend, we stretch the tip of this band domain in the current direction. Now, if we now put this into a constriction, the situation becomes more complicated, because now we have an inhomogeneous current distribution here. And so we have current that also pushes through the sides here. And so what that results in is that the end of this band domain gets blown up, kind of like a bubble. And just like when you form a bubble, you get then at some point the necking instability, and you can, pull, bubble off from this end of this domain wall structure here. And that's pretty much what we saw in the experiment. We see this also in the micromagnetic simulation. This is a micromagnetic simulation where the sample is much smaller, because it's hard to do it for the size that we actually experimentally measure. So here, full band domain doesn't fit into this constriction. It's just the tip of a band domain. But if you now apply a current, what you see, it gets distorted. Now it gets very complicated and very messy, so not as nice and easy as a simple schematic that I showed you. But when we switch off the current, we see that we are left off with magnetic skyrmions in the end that are very high energetic here and still moving around. Now it turns out we were also interested what happens if we use larger currents. If we use larger currents, actually, once we apply the current, the torques are so large that they destroy these domain walls altogether. You get rid of any magnetic domain structure. You pull all the magnetization into the plane of the film. But when you switch off the current, now out of this, you can still again nucleate magnetic skyrmions this way. So this means you don't have to have a pre-existing magnetic structure to generate magnetic skyrmions using current pulses. And indeed, we see this experimentally. So we took the same kind of trilayer that we had before, removed the constriction, replaced it with a non-magnetic wire. Now we need larger currents, so we just use pulsed currents instead of DC currents. But when we do this, with each current pulse, we can see that we can generate skyrmions on demand here in these films. Okay, so now that we know how to create skyrmions on demand, we can study their properties in more detail. And so one particular thing that we were interested in was the Skyrmion Hall effect. Now, most of you, or I hope all of you, are really familiar with the ordinary classical Hall effect, where what happens is, if you look at the motion of an electric charge, let's say an electron, in the presence of a magnetic field, then there's a Lorentz force, which means that there's a force that's perpendicular to the direction of the motion of the electrons. And we know this gives rise to charge accumulations on the edges of current-carrying wires. And we use this to characterize charge densities and the nature of charge carriers and so on. Now it turns out, if you look at the motion of skyrmions, there's a very similar physics at play, where you get a transverse force given by, that depends on the topological charge of your skyrmion. And it's essentially identical with what's known as the Magnus force. The Magnus force comes about if you have a rotating object, and now because you have different airflow on one side versus the other flow, it gives rise to a curved trajectory of a rotating object. So if you're a bad golf player, you know that as a problem. But if you're a good soccer player, you can take it for your advantage. And so I want to show you an example, which is demonstrated by an expert on the subject, famous Brazilian, Roberto Carlos. You may have heard of him. Here he demonstrates this effect together with some French colleagues. So he has the soccer ball here that's supposed to go into a goal there. There are a couple of colleagues in the way, and using the Magnus force, you see it much better now. You can easily achieve this, goal. So you may now ask yourself, excuse me, what does rotating soccer balls have to do with magnetic skyrmions moving? What is rotating here? Well, so think about it. If you move a skyrmion spin texture in a magnetic material, you don't really just take all the spins and move them. The spins are local spins. So what you have to do is you have to rotate spins in order to move the spin texture through your magnetic material. And if you do that, what you see is that at the top, the in-plane spins rotate counterclockwise, while at the bottom, the in-plane spins rotate clockwise in order for moving the skyrmion from the left to the right-hand side. So by moving the skyrmion, it looks to the in-plane spins as if they are exposed to magnetic fields with opposite directions, which makes them spin in opposite directions. And so essentially, for a moving skyrmion, it looks like there's an effective magnetic field gradient across the width of the skyrmion. And this field gradient can then couple to the magnetization in the center, and that gives rise to a transverse motion. And so you can actually calculate this by taking the Landau-Lifshitz-Gilbert equation, and by assuming a rigid skyrmion model, you can come up with an equation of motion known as the Thiele equation, which has three terms. One term describes the force acting on the skyrmion due to the electric current that we pass through the sample. And so this tensor will depend on exactly the physics that we use. But in the case of these Niel skyrmions and the spin-orbitals that we use, this force is in the same direction as the applied current. Then you have a dissipative term, which is just proportional to the velocity here. And then you also have a gyroscopic term, which depends on this topological charge of the skyrmion. So this is the Magnus force that pushes the skyrmion in the perpendicular direction. And if you make now a micromagnetic simulation of a skyrmion in a rectangular slab where you apply a current along this rectangular direction, what you will see is that the skyrmion initially will move sideways until it gets close to the edge from which it is repelled, and then it starts moving more in the direction of the current. And you can, using this Thiele equation, actually calculate how big this sideways motion is. The ratio of the transverse to the longitudinal motion is just given by 1 over this dissipative factor, where alpha is the magnetic damping and d is a constant depending on the geometry of the skyrmion, the size of the skyrmion. Okay, so can we see this actually in an experiment? Yes, we can. So here we generate skyrmions up here, and we have a homogeneous current in the whole width of this wire. And what we see is indeed that these skyrmions move at a well-defined angle with respect to the current. You see that they all move subsequently down. This kind of jumpy motion is because we use current pulses, and so it's like, you see the position of the skyrmion after each current pulse. So we can analyze this further. We can also now reverse the magnetization, which reverses the contrast. Instead of having bright skyrmions on a black background, you have dark skyrmions on a white background. It reverses the topological charge. Remember, the topological charge was not in the magnetization. And lo and behold, it means that the skyrmions move in opposite directions, transverse to the current, because the topological charge is reversed. Now, as I said, these movies are made by having pulse currents. We can see with each pulse how the skyrmion moves, and we see with each pulse it moves the same amount in X and the same amount in Y, which means that for these currents here, we are in what's known the flow regime. So the skyrmion moves kind of independent of any defects in the material. If we have a smaller current, what we see is that the motion is much more irregular. Now, there's no well-defined transverse motion. There's a random up and down motion. You see this here particularly well. And if you look careful, you see that the steps in X and Y are much more different with each current pulse. So this is now where we are in what's called the creep regime, where the motion is much more determined by the random pinning potentials in the films rather than by the drive of our skyrmion motion. And so at that point, we don't have a well-defined transverse motion anymore. So if we put it all together, we can get a diagram like such, where this is the Skyrmion Hall angle, meaning the angle of the propagation direction with respect to the applied current. This is the magnitude of the current in positive or negative direction. Then the different quadrants is these two are for negative fields, these two are for positive fields. Oh, sorry, the other way around. This is for positive fields, this is for negative fields. And you see that for small currents, there's no deflection. Then as the current increases, the reflection becomes larger and larger until it saturates at high enough drive. And so at high enough drive, we can now compare the deflection that we have with what we expect theoretically from the analysis that we had earlier. So this constant d is given by the diameter over the width of the Skyrmion wall. So for our samples, we know that the diameter is about 1 micrometer. So d is around 60, meaning that we expect the Skyrmion Hall angle of around 40, and we measure about 30. So within, the uncertainties of d and alpha, that's actually pretty good agreement. The other thing that we see is if we go to higher fields, the diameter actually becomes smaller. The Skyrmion shrinks a little bit. And so when we go from 4.8 Ørsted to 5.4 Ørsted, we see that the Skyrmion Hall angle actually increases, which makes sense because as this becomes smaller, d becomes smaller, and so the Skyrmion Hall angle should increase also. So this is very nice. So indeed, this fits nicely together. And if you look at numerical simulations of Skyrmion motions and random pitting potentials, you see very similar behavior where you have a linear dependence of the Skyrmion Hall angle with the driving force, which then in such a way is when the driving force becomes comparable to the pinning forces in your material. Okay, so this really brings me to the end of my presentation. Let me skip this. What I hope that you take away from this is that you can really generate magnetic skyrmions relatively easily in these magnetic heterostructures. You can then make complicated structures like here we have these winding wire, and if you pass a current through it, you see skyrmions moving along the wire. So this is almost like this racetrack memory idea, except here this movie is taken in the creep regime, so the motion is stochastic, so it is not really a very good memory device in this sense. But anyway, this is the group of people that did the work while I was still at Argonne. In particular, this young guy, Wanjun Zhang, was the main driving force for this work. He's now a professor at Tsinghua University. Here are those people. Wanjun Zhang was the main driver. There were a couple other postdocs, Wei Zhang, Manjin Jungfleisch, more senior people. Ola Heinenen did a lot of the micromagnetic simulations that I showed. Susanne Feldhaus was directly involved in the MOOC measurements. The samples came from Gu Kwang Yu and Kang Wang's group at UCLA. Then Zixiao Zhang and Yang Zhu did some micromagnetic simulations related to the Skyrmion Hall effects. And Zhao Wang was involved in those measurements as well. Here are the conclusions with relative relevant references if you want to read more about this. In the interest of time, I'm not going to dwell too much on it, and I'll be happy to answer questions.
Thank you, Axel, for this very nice talk. I will start taking questions now. As usual, people can ask questions in 3 different ways. You can raise your hand here at the Zoom app, or you can write the question here in the chat, or you can also ask questions in the YouTube transmission. So there's the first question here from Diego Frota. It's written here in the chat. I can read it to you. Can you talk about Skyrmion dynamics simulations by Monte Carlo Metropolis algorithm instead of the micromagnetics approach? Is there advantages of the Monte Carlo Metropolis over the micromagnetic simulations?
Very good question. I'm not sure I'm the best one to address this question, since I really don't do the theoretical simulations. But what I would say is, for example, these simulations done by Charles Reichert in Los Alamos, he assumes that these skyrmions behave like individual rigid particles. And so if you want to look at a whole bunch of skyrmions and how they interact and what, that you can much easier do in these kind of idealized numerical simulations, which is probably more similar to this Monte Carlo kind of ideas that you may have. Certainly, you would not be able to make really large, interacting systems like this with micromagnetic simulations, for example.
Great. So let me take a question from the YouTube. So a question from Luan Verissimo. The Jaluzinski-Moria interaction breaks the inversion symmetry. Are there another hidden symmetry that protects the structure of Skyrmion as a topological excitation?
So I wouldn't say that the Jaluzinski-Moria interaction breaks the symmetry. It's the other way around. Once the symmetry is broken, you can have the Jaluzinski-Moria interaction. That's how I think about it. But it turns out you don't have to have a broken inversion symmetry to get skyrmions. You can also get skyrmions by frustration with next nearest neighbor interactions and things of that nature. But it helps if you have the broken inversion symmetry. It makes it easier. Especially also, it means that you get skyrmions with well-defined chiralities. If you have different chiralities, if you had, for example, a system with different chiralities here, then that would mean that you would have skyrmions, some of which move in the direction of the current, while others move in the direction opposite to the current.
All right, so there's another question here from Ramon Cardias. Ramon?
Hello, can you hear me?
Yes,
I can hear you well.
Yeah, thank you, Professor Hoffmann. My name is Ramon. I'm a former student from Federal University of Pará. I did my PhD in Uppsala University, and I work with magnetism. And I'm afraid that my question is from the theoretical point of view as well. I'm sorry for that, but if you have the information, I would like to know. So I think in 2011, the group from Jülich, they published this Nature Physics, where they found evidence for this ground state skyrmionic phase for item iridium 111. And theoretically, they showed that the four-spin interaction is responsible to stabilize the skyrmionic phase. And you told in the beginning of your talk, like a simple Heisenberg Hamiltonian with the J's and the D's. But we know that in non-collinear regimes, it's not that effective that you go up to the second order. You need maybe fourth order, sixth order interaction, like 4-spin, 6-spin maybe. And I was wondering if you know how important those you talked about a lot about micromagnetic simulations, but if I'm thinking more in like an atomistic model, how important those high order interactions are to the description or the dynamics of those skyrmions.
Well,
and
okay.
Yeah, sorry.
Then, yeah, sorry.
No. Yeah, a follow-up question is, if you know this, how would those high order interactions would be taken into account in the micromagnetic model as well? Because I never heard of. Thank you.
Yeah, no, I think it's a very good question. I mean, ultimately the question is, okay, experimentally we see a certain structure, right? And so now what is the minimal model that describes this? As I said, you can get skyrmion structures certainly also from the competition of nearest neighbor with next nearest neighbor interactions. Now the question is, can those models also give you a well-defined chirality, right? And so the other thing is that we understand reasonably well where the chirality of the interfacial Jaluzinski-Moria interaction comes from. It's essentially, you look at these two spins that are coupled by an intermediate element in the heavy element layer, and they set up well-defined triangle that then defines a surface where the Jasinski-Maria interaction is perpendicular to it. So you can calculate that fairly straightforward. I mean, I don't know in the paper from Jülich if they essentially just fitted their results that they get from their calculations into a Hamiltonian that has the nearest neighbor and next nearest neighbor interactions, or if they really determine these interactions directly from the ab initio calculation.
Yeah, if I remember correctly, as far as I'm concerned, those interactions I never seen them been calculated from first principles, only like fitting with the energy, and I'm almost sure that they did the same. They put out a model. They had an experimental result showing that the ground state is skyrmionic, and then they put up like a Hamiltonian with just the J's and the D's, and that would not give you the ground state. But if you would put out the force interaction, then that would give you the skyrmionic phase.
Yeah. Okay. No. So, but that may very well be then very valid in their case. Also, I mean, in those in the structures that they looked at, the skyrmions were much smaller than what I discussed today, right?
Yeah, exactly.
So certainly when you have skyrmions with diameters that are close to atomic sizes, I can easily imagine how next nearest neighbor interactions become much more important. But the structures I discussed today, for example, these are like a micrometer in diameter, right? So these next nearest neighbor interactions gets much more washed out in that sense.
Yeah, makes sense. Mm-hmm. Thank you.
That's how I would look at it, I think.
Great. We have a question now from Antonio Azevedo. Antonio.
Axel, thanks for the nice talk. Actually, you said that the threshold for the current threshold to move the skyrmion is much smaller than the threshold current to move domain wall, right?
Okay, I have to preface this. This was for moving a skyrmion lattice in iron silicate. So if you look at the threshold current of the skyrmions in our thin films, that's not that much slower or less.
Ah, okay.
If that's what you were going to ask next.
Okay, thank you. The other question is, what does limit the size of the skyrmion?
You mean maximum or minimum size? Minimum size? Well, okay. I mean, minimum. They can be very small, like what we just mentioned before in these.
From the fundamental point of view, what does limit the size? And
well, so think of having a skyrmion, one atom pointing up in the center, then you have like 6 around that go in plane, and then you have the next layout. That's kind of the smallest you can think of, right? And that's what they've seen with spin polarized STM measurements in the Hamburg group. That's what this iron on top of iridium essentially was like. So that I think is kind of the smallest size you can think of. Now, what the question is, can you have really small isolated skyrmions and then still manipulate them?
that's right.
That's a different story, right?
Yeah.
And so the smallest isolated skyrmions that I've seen are a few nanometers or so. And mostly those are in ferromagnetic systems where you're close to the compensation point. And the reason for that is in these ferromagnetic systems, the dipolar interactions come into play, and they blow up your skyrmion system much bigger. So in our case, it's mainly the dipolar interactions that make the skyrmions as big as they are. So if you can get rid of these dipolar interactions, you can make them fairly small and still stable.
Oh, okay. Thank you.
All right.
Okay, now the next question is from Ivan. Sorry, I can't see your last name, Ivan. You can ask your question.
Hi, my name is Ivan Miranda. I recently got my PhD from the University of São Paulo. So first, I would like to thank you for your very nice talk. My question is about the Skyrmion Hall effect. So if you think on racetrack memory, as you quickly show in your last slide, can you? How do you prevent the Skyrmion Hall effect in this system, for example? Because if the Skyrmion hits the wall, it will not be very good for applications, for example.
Well, okay. So it's not entirely clear whether the Skyrmion Hall effect is good or bad. Let me say the following here. So what you also see is that as the Skyrmion is pushed closer to the edge, it actually moves faster in the direction of the current. And essentially the way how you can think of is the repulsive force gives rise to the Skyrmion moving in this direction, right? So on the other hand, it may then also mean that you can only move the Skyrmion so fast, right? Because if you have too much of a driving force in this direction, then the transverse force may be bigger than the repulsive force, and you may push it out of the boundary. But so one way how you can possibly avoid the Skyrmion Hall effect is by having Skyrmions in antiferromagnets. So in antiferromagnets, you can then think of, remember I said if you reverse the magnetization, the topological charge is also reversed. So you can think of having two Skyrmions with opposite topological charges bound together. And so then if you push those antiferromagnetic Skyrmions, they move in the direction of your driving force, right? You could also imagine maybe you could have the current perpendicular, right? And then the Skyrmion moves already in the direction that you wanted to move anyway. And it's not clear that the Skyrmion Hall effect is something to be avoided or that can actually be useful. To be honest,
Okay.
what I would say is, at the end of the day, it turns out that there's maybe not that many advantages of using Skyrmions compared to domain walls in racetrack memory devices. So if you just have a linear memory device, you might be better off with domain walls because it puts less constraints on the materials that you use. Where Skyrmions really become interesting is if you think of devices where you move your spin textures in 2 dimensions, right? And where this additional degree of freedom can be used for some logic functionality, for example. And I think then having the Skyrmion Hall effect may actually be a good thing. What do I know?
Thank you very much.
Sure.
All right, so let me take a question from YouTube. There's a question from Elena Petrilli. What is the state of the art of applications in devices using Skyrmions? Already something on the industrial scale? That's the question.
No, nothing is in real applications, and I don't see it happening anytime real soon either, to be honest. Even with domain wall structures, this racetrack domain wall idea has not necessarily progressed all that much, because by encoding information in mobile spin textures, you face a big problem in that you have to have the spin texture has to be stable against thermal fluctuations, and the position of the spin texture has to be stable against thermal fluctuations. And that is really a hard problem. At this point, I think looking at the basic physics is the most interesting thing you can do with skyrmions. And even though I did mention that the community got excited about it by its applied potential, ultimately, I'm not sure that's where it's at, but I may be wrong.
All right, so there's a question from Belita Coiler. Belita.
Hi, I like to talk very much, but I'm not an expert. And so I ask a simple question. What's the total spin of this skyrmion?
The total spin?
Yeah.
Well, okay.
Magnetization.
Well, that depends on the size of the skyrmion, right? And the magnetization of the material that you're looking at. So that may vary a lot from material to material.
You mean it doesn't have a well-defined statistics? It's not a fermion or a boson?
No. It's a really much more large particle. So everything I've shown you can be understood, fairly classically. You don't need any quantum.
Okay.
Well, except for magnetism, being a quantum effect, but
No, I think it's interesting that they are repulsive. The interaction is repulsive. You can see from the simulations that they tend to be as apart as possible.
yeah, but that I think you can essentially understand in terms of well, let me see what would be a good. If you look at this picture, just imagine that this is the center of one skyrmion, this is the center of the other skyrmion. If you push them together, it's like winding up a coil, right? That's essentially what it is.
Okay. Thank you.
Sure.
So there's a question here in the chat from Lucas Palhares. Let me read it to you. I have a question. First and foremost, thank you, Dr. Hoffmann, for this wonderful presentation. I would like to know if the domain wall structure of the skyrmion, Néel type or block type, affects the Skyrmion Hall effect. In other words, is the deflection caused by the Magnus-like force on the skyrmion? Is it different for different types of wall structures? Thank you.
So very good question. So the short answer is no, it doesn't matter. Because if you think of these spin structure here, so this is what's called a Néel skyrmion. So I didn't go into details there, where the magnetization in between the center and the exterior points in a radial direction. If the magnetization rotates differently, so that it's in a tangential direction here, that's what's known as a Bloch skyrmion. And this is an analogy to Bloch and Néel domain walls, where in one case the magnetization rotates in the plane of the domain wall, and in the other case perpendicular to the domain wall. But you can get one from the other by simply rotating the in-plane component of the spins by 90 degrees. So in terms of the topology, they are identical. And what this also means that in terms of the topological charge, there's no difference, right? And all that goes in here is the topological charge. So it doesn't really matter whether it's a Néel or Bloch skyrmion. Essentially, all that matters for the topological charge is the magnetization in the center up or down. Because that's essentially what the topological charge means.
All right, so there's another question from Jose Abel Hoyos. Abel, you can ask your question.
Hi, thanks for this wonderful seminar. I have two questions actually. One one is about this diagram, this density plot. Is the skyrmion really shrinking when it propagates, or is just a cartoon?
No, that's very well observed. This is a real micromagnetic simulation, and yes, it's shrinking. And part of why it's shrinking is, as I said before, that the size is determined by the dipolar interactions. And so the closer it gets to the edge, it sees a different stray magnetic field, right? Because all the magnetic material here on that side is missing. So the stray magnetic field becomes smaller, and therefore the skyrmion also shrinks in size as it gets closer to the edge.
Yeah. The other question is from a theoretical asking about experimental details.
Yeah.
Could you just say some words about how do you do this image? And also, could you give us the time scale of these movies that you just shown? Are the skyrmion propagating like nanometers, hundreds of nanometers per second? And how long does it take to do these images? 1 day, 1 hour, 1 month, an entire PhD?
Okay. So the technique that we use is magneto-optic imaging, and the movies that you see here is like real video frame rate. It's real time, you know. So each skyrmion is about a micrometer in size. So that kind of gives you the velocity. Unfortunately, it's, well, what did you want to know? If it's 100 nanometer per nanosecond or something? No, it's not anywhere close to that. It's you know, a micrometer per second, right? So it's fairly slow velocity, because the current is also very low. But yeah, it doesn't take a lifetime or a full PhD. You can get these easily in a day.
Thank you.
All right, very nice.
I would say if you have smaller skyrmions, you may need a different technique, let's say X-ray based imaging techniques. So that's a little bit harder. That may take longer, but you can still do movies within, you know, the time of a beam time.
Thank you very much.
Sure.
Okay, so it seems to me that this was the last question. So I would like again to thank you, Axel, for this very nice talk. I would ask everyone to open their microphones and to give Professor Hoffmann a hand of applause for this very nice presentation. And thank you. So thank you very much.
Thank you. It was a pleasure. I really enjoyed you know, the presentation and the questions. And
So I will stop the YouTube transmission now. All right.
Okay, bye-bye.
All right, take care. Get back to work, Antonio.
That's right.
I see you again.